Okay, so I'm back. I mean, something super weird was happening. The capture wasn't following my screen anymore for some reason. Anyway, trying to start again. That's tonight is very bumpy. I'm sorry for that. Okay, so last thing was it wasn't working anymore. So what I did was I'm trying to save the D register, because the less register I need, the bigger I can make them, and the faster hopefully we will be. So I think that by adding an operator that allow me to swap B and C, I can dispose of, I can do without using the D registers. So that's the theory, because I try to write the sigmoid, but it's not working. So debugging. So I'm gonna print the registers, and I'm going also to print the op, because if I can see the op, I don't know where we are. All right. I'm impressed that whoever is watching, you're back again. Thank you for your patience, because tonight is really super clunky. I am just completely sorry. Between the connection and the streaming setup, nothing works tonight. The code was going okay, but so far, because now it's not working anymore either. As you watching, what is happening is, so I had a swap BC, because adding this operator swapping B and C make it possible for me to compute the sigmoid with only 3 registers, or at least that's what I think. And now I'm trying I implemented it, and I'm trying to debug it, because it's not working anymore. So just trying to figure out a way to have a readable print. So this doesn't help. Maybe just yes, maybe just like that. Okay, it's not so bad. So now what we need to do is to compare this output with, let's say, a nice P and Q, like that would be interesting. So we need to figure out where it starts also. So here I have P and Q, and so min const 3 is the first thing that we do, and we are starting. So I'd like to see the X that comes into the machine before we start. I think it's a super negative value here, because we are getting into the negative clamping. So that's gonna be X. Yep. Again. So X is yeah, that was right. X is super negative, and what is the error we don't get? Yeah, we have this, so this is not what we need. Okay, so these are, no, sorry, blah, 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 blah. P and Q here, these are the correct values, and we have P actually here, and Q seems to be Q we never get Q, so P is fine. And we have put P in C, so that's fine, and it's preserved. And we get it all the way till the end, that's nice. But something is wrong in computing Q. So this gives us a good hint. So where is Q? Okay, so we do the mule. So swap BC mule. This gives us P. We're moving X2 back in there where it was before. We're moving P into the C registers, and then we're const 11. Oh yeah, here we have a problem because we are multiplying the old value of P with the constant 11, which is not what we want to do. We need to move X2 in A. Nope. It's not it. So, oh, yes. Because here I have overwritten P before preserving it. And so, yep. So actually what I would need here is the rotation of the 3 registers. But yes, okay, it's fixed. Good. So we can do the sigmoid with 3 registers only. And I know that, I'm pretty sure that the hyperbolic tangent will work the same. That's super good news. To be honest, the next, if we wanted to get further in this direction, the next one to look at would be exponentiation. But exponentiation is a bit more complicated because there is a way to compute exponentiation which is relatively easy to put into a vector form. But I think that it will probably need more like 5 or 6 registers. And so I'm not sure that it's worth the trouble. What was it called? Faster math? No, .NET, no thanks. Maybe that one then. Yes, this is what I was looking for. And if I look at exponentiation, so the typical way to compute exponentiation is to split x between an integer part and a floating point part. And so exponentiation of a plus b is exponential of a times exponential of b. And if you use the base 2 exponentiation, doing the exponentiation of a where a is an integer, positive or negative, is super easy because it's just a bit shift operation. I mean, it's a bit of float manipulation and yeah, basic. I mean, it's easy. It's fast. It's not easy, but it's fast. And then you just need to compute. The exponentiation with an approximation on a given interval. So sometimes you take half to half or 0 to 1, and so yeah, here's that's for double So I think if I remember correctly, they're using a rational approximation for double precision, but they are happy with a single precision, with a polynomial in single precision. And we know that polynomial we can do with probably, I mean, we don't know that, but I think we can do with 2. So we have more of these Horner polynomial form here. And so to compute exponential of f, base 2 exponential, well, basically that's it. 1, 2, 3 intermediary variables plus x. And it looks like they manage it. And I'm not even sure that E part is actually needed. So built-in floor. So that's so this. If you save, you need to hold x. At this point, you need to hold x and I part. Then you need to hold I part and f part, but you no longer need x. You actually overwrite x here. So here you need two. You need 2 position. This bit fm float init exponential exponent. It has to be exponents. So that's the bit where you do the bit magic, the bit magic shifting to transform the I part into the right power of 2 just by shifting bits. And then you don't need I part anymore, which is super interesting. Then we have the polynomial part where we just need to hold onto the f part and x, and then we multiply. So it's probably doable with 2 or 3 registers. So that's actually pretty tempting. Okay, let's give it a shot. I want to give it a shot because if we, I mean, I'm curious. I'm curious to see if this can be, I mean, how good or bad it can be compared to couple of implementation. I mean, I want to experiment. I want to play. It's fun. So that's exp2 float for x32. So that's, oh yeah, it's C. Okay, it's a C function. So built-in floor f. This will be so I won't need that. So I will need let I part equals f32 will be x plus half floor. Let's see. It has to always go to the left, and so yes, it's okay. This is the test. H minus 3 dot h minus 3 dot anything go to minus 4. So that's the right one. Okay. F part will be, I don't need this. F part will be x minus I part. This guy can go away. So this bit, so what does it do? So it builds, I think, 2 to the power of I part, where I part is an integer. So we need so I will I will need to make I part an integer. And so in Rust we have in F32 we have a couple of functions, or maybe just one function from bits, maybe from F32 primitive floor sail around. Yeah, more than a couple of them. From bits. So that's transmutation from U32. It's not what I'm looking for. I'm looking for a function that split the float into its signum, its mantissa, and its exponent. And there is the function, the opposite function. Also, 2 bits, but not there. So let's have a look. It has a name. Anyway, I mean, if we don't find it, we can still we can manage. We can manage. Plus, we have this constant. And do we have the? So that's the number of bit. Yeah. Approximate number of significant digits in base 10. That's approximate number of significant digits in base 10 is the same thing, right? Oh no, sorry. Okay. So we have the I part. We will make it show. So we will need to shift 23 times to the left, but before that, the exponent should be 2 to the power of 2. Yeah, there is a shift with the 0 offset being 127. Okay, exponent bias. That's a bias. So if we have, so we need to do exponent will be I part as E32 minus 127. So that's the exponent, and I will shift it to the left 23 times. And that I can cast. Do I need to cast? No, I don't need to cast. Yes, I need to cast this as F32. And so this should be 2 power I part, hopefully. Yeah, that bit. I can remove this. So then we have this. So I need to grab the coefficient. Yeah, okay, that's fine. No GPL. No GPL, no worries. exp2f. So static const float. Let's simplify this a bit. We will just call it an array of an array. So let so const that equals okie doke, and I don't need these guys. I'm not sure if they hurt actually. And finally, so this part I don't need to change, and that part, so here we are casting yeah, that's x times, I'm not sure about this bit, to be honest, because this part will be, I think there is a property that we don't use. I wonder if this part if x stays in the right range, like between between half and 1, then we can maybe just OR these two. Well, no, sorry, I'm lost. Okay, I'm lost, but I think I may have an exponential function that I can try. What's wrong? Yeah, syntax. So this I will declare as f32. Yes, 1, 2, 3, 4, 5, 6, 7. Okay. No problem with this. And yeah, so that's a constant. So what is missing? What is missing? What is missing? Main, main function. Yeah, of course. Okay. That's yeah, a bit dirty, but I'm bored with the error message. So exp2f, I can test this function. I can test this function with text test exp2f. And first I'm going to test my function against x dot exp2. So it's actually 2 to the power of x. Is that right? I think so. Prop assert ec. Let's prop assert. Ah yeah, I was doing close enough in the other ones. Prop assert. And I see, yeah, same, really close enough. So exp2f, exp2f. I need to import it because I'm in submodule, and this has to be powf. You must specify a type. Let's test this. Test 2f. Alors, failing input x equals 0. Okay. Okay. X equals 0. So let's see x I part, F part. So we should see 0, 0, 0. Super interesting. exp2f. So x is 0, I part is 0, f part is 0. Fine. Then the power of 2. So unless I'm mistaken, we'll see. We'll see. So we have a super negative value. Is it what I was expecting? Not really. No, not really. So I part as is32 will be 0. Minus 127 will be minus 127. Offset 23 times to the left. Let's see what that is. So this should be an integer. It will be value impossible to interpret. But what we're going to do is I'm going to print. Yes. Print line, print. Oh, yes, I know. I know what I did here. This is a conversion. What I need is here is a reinterpret cast, which is f32 from bits. Okay. Parentheses. Expected u32 find e32. Okay. So so I need to cast this as u32, I think, and then offset it 23 times to the left, and then make it a float. Is interpret as start of generic. Okay. Try again. So -4. Really, that's interesting. Not exactly what I thought. Okay. Debug more. So debug I part as e32. Key. I part as e32 minus 127. So that should be, this should be minus 127, yes. Then cast this as u32. This will only be readable. No, because it's yeah, it's okay, I remember now. So we have 8 bits in the exponent. So we need here to minus 127 as u8 as i8. So this will make it small, because we have all of these one to the left that we don't want, and these are the one, I think, which are problematic right now. So if I'm doing now as i8 as u8 as u32, and I want to see this in binary or in X. binary. Unnecessary parentheses, that's fine. Okay, this is wrong. Definitely not what I need. So let's try again. I part is 0, minus 127. This is this has to be 100 minus 127. So as E8, sorry, I8, shifting to French. Minus 127. Okay, so I have this value. It's negative. I need to interpret it because it's full of 0 to the left. So, okay, what if I do? Okay, let's check already this. That's still 127. Okay. Now 127. If I interpret this as U8, and I want to see it in binary. So the what is it? Is it right? Yes, it's fine. Yes, this is actually correct. I thought it was wrong, but it's actually correct. It's not the first negative value. The first negative value would be 1 followed by 7, 0. It's the one after, because we can encode minus 128, and we are interested in minus 127. So that value I can shift to the left. It should work. So 23 times. Attempt to shift left by with. Okay, so now it overflows. Do I still need to cast as U8? I'm casting as I8 and then as U8. But yeah, I have to do this because if I'm not going through U8, I'm going to lose. Okay. So now this is pretty good because we have put this all to the left, and we have, I won't count them, but I gather 23 of them. And now I can reinterpret this bit as a float. F32 from bits. Nope. Okay, so print, that's a 4. Okay, still a 4. Nope, this is not right. I don't think this is right. Okay, let's try something else. Let's try up. So of 0, and I want to print So it has to write into epart, and I want epart is a unit. Epart is what? Epart is a union that has a float. So float is f, right? Okay. What did it tell? Request from a ref in something not a structure of the union. Really? Ah, yes. I need a couple of includes. Faster math or FM internal, I guess. If I remember correctly, it was in FM internal. Faster math include FM internal. So I'm looking at the union. Here we go. That's union. UFET, yeah. What? We need standard types, and we need print stdio, stdio.h, and we need the standard types. I never remember when they are. C types. Let's see. Nope. Overview of system types. uint 32. stdint. Okay, I don't need. So the function, yeah. So the function that I want, well, that's basically that's it. Oh, so I think I see the problem. The bias is a plus here, and I'm doing a minus. So that's my problem, really. And I will add the missing couple of constants. Not sure which one I need, but bias for sure. Try again. And alignment, I don't care about it. I don't care about the alignment. Attribute. Okay, dot out. 1. Okay, thank you. That's closer to the truth. So I think the problem is just here. Let's try again. Before we are doing C, when we are doing Rust, exp. So now 2 high parts equals 1, which is what we were expecting. So we have an overflow. Okay, so now this bit seems to work. I'm gonna comment that terrible part, and so it says that we are trying to nope, not anymore. So what is it computing? It's taking a super negative value of x So the I part is obviously very negative. So let's see what are parts. Debug tuple parts. True for e parts equals 1. Is it true? It should be 0 actually. It should be 0 because it should be 0 because we are far in the negatives. Oh, except no, it should be far in the negative. And because the f part will be 0, so the contribution of the f part should be 0. And it says it's 1. Yes, because we have these terms. So okay, so x is 1. So I mean, we need one of these two guys to be 0, and it won't be this one because x is 0 because it's the f part. No, f part is 0. Whoa. So f part is 0. So that leaves us with x equals this guy, which is 1. So x is 1. And so 2 I parts has to be 0. Plus, it's actually the 2 to the power of a very big negative number. So it should be 0. So we still have something missing here. Let's try again with our bit of C. We probably have a bit of subtle or not subtle. Anyway, something that doesn't work. One. Okay, so I think we may have a different problem here. The question is okay, so we need to read the documentation. Because from my point of view, this means that this approximation only works for a given range, for a given range of values, and we are probably wandering out with it with these big, I mean, very negative values. So let's try. I want to try something else while we are at it. I want to try. I would like to try. I want to make sure. And so this should be the implementation from standard library and include math. I can do that. And I need to link it now. 0. Okay. Okay. So there is something I don't know about this library and its exponentiation implementation. It has to have some limited range of validity for x. And it doesn't say so. That's a double one. Optimizer for an implementation of exp2f. That's Vim. They are based on the corresponding implementation from CFS math library. Code business prepare using internal compiler facilities whenever possible and assuming little Indian single and double precision math. Okay. What else do we have? Extended precision, single precision function. Let's have a look, see if we can find some information. Okay. Okay, which it kind of makes sense. I mean, exponentiation, if you're too small anyway. If you're too small, it doesn't mean anything. I mean, it's 0. If you're too big, it's infinite. It's something that you can no longer represent as a float. But the good thing is here we know the domain, and I mean we could have guessed it. It's not defined out of this. I mean, I think. So the way to deal with this, I guess, would be to clamp x min 127, 127 max and I think at least it shouldn't, because here it's breaking. I mean, if I part is above 127, then this will be too big to be stored in the I mean, it will be a an exponent we cannot use for a single precision float. So okay. Let's fix this. And cargo test. Hey, that's pretty good. So we have a Rust reference implementation for 2 to the power of x. And from there, I mean, this thing looks bad in Rust, but it was actually looking better. It was actually looking better in C, and in assembly, it actually looks. I mean, if you don't look too closely at it, you don't even see that that it's doing something relatively dirty. Because basically in assembly you just call I mean, there is no typing, so it's whatever you use as a function that as an operator that as an operator as an opcode that choose the type of I mean, reinterpret the bit from the registers in the way you want. So what would it take for us to put this into our VM? So first of all, in terms of number of registers, this we can do in place. I think we already did that actually, but this we can do in place. Here I need one register for I part plus X, then F part and I part. Then this replace I part, so it's still 2. Then here I will need an accumulator plus, so I need 3 registers and then 2. So I can do this with 3 registers, I think. But I need a couple of functions of primitives that we don't have yet. So we need the floor primitive, and we need this ugly thing, but we will make it a primitive. We will not, I don't think I will detail the shift and etc. etc. So let's try again. Let's try it. So we say that we want so I have this, we need floor, okay. We need floor and we need power of, so it's 2 power of constant. Not, yeah, so it's 2 to the power of an integer. Okay, it's positively ugly as a name, because what it actually does is it takes a float, it converts it to an integer, and once it's done, it does the bit shift. I mean, there is a mantissa, the bias, it does the bit shift and makes it a float. But actually, yeah, 2 to the power of int. Okay. Okay. Alright, so floor. Let's implement them. So a bit of debug. Up floor will be regs of 0 equals regs of 0 dot floor. This is the easy one, and the other guy will do this ugly thing that we spend so much time on. So that's reg register number 0 equals f32 from bits regs 0 as e32, so that's our conversion. Then we add 127, that's the floating point bias. We come back to u32 to avoid, I mean, do I need this one actually? I don't think so. I think I can dispose of this specific cast. Then we shift it 23 times to the left, And finally, we reinterpret it as a float. Okay. So now, if I want to implement exponentiation in my VM, we need these constants. I already have one. So how do I do that on this screen? Okay, let's make room first. So exp2f exp2f is a program. Up, closing. I will need some constants. Yes, I have disabled the formatting in these, so I need to do it by hand. So my constants are these. I need these 6 constants. Yes, consts here. Once, twice, and now for the fun part. We'll take this, put it down there, so I can have it on the screen. Okay, so all right, we also need 0.5 as a const. 0.5. So first we add, we do x plus 0.5. Do I need to preserve x? Yes, I need to preserve x. So I'm moving x, which is in A, to B. Then I'm doing, first we do the clamping. So we need 127 and minus 127. So the clamping will do max of min first of A with the first constant, so it's min const. So the first constant is 1 because 0 is 0 and 1 is 1, so this is actually 2. Then max const with 3, so that's the clamping in minus 127 plus 127. From there on, I'm moving x to b to preserve it, because I will need it there. So I can floor to compute I part. So that's clamping, it's pretty self-explanatory. So b equals x and a equals I part. I need to do x minus I part, and I need it in. So if I do sub here, I will put this will make I part minus x in A, and it's not what I want because I will have overridden. I part. So I need to move stuff around. So let's move. I'm moving I part in C. This is not super nice. I'm moving yeah, I need to permute the three of them actually. So I moved A to C. I'm moving C in B. So that's B equals nope. So C equals I part. So now I must write in A, and I will put A equals whatever was in B, so X. And finally, I will put in B whatever was in C, so that's B equals I part. Okay, for this rotation, and then I can sub, and now I have A, which is X minus I part. Maybe there is a faster way to do this, or maybe I need some extra operators like flipped sub, but for now it will do. So I have I'm here, and I want I want I part back in A to be able to do the 2 to the power of. Or maybe I will, because what do I have in A? I have X minus I part. I have F part. So I can do the polynomial part right away. And the I part, it's in B. Okay, it's in B, so it's not good. Because in B I will need to put F part. So should I swap B and C? So if I do this, I'm putting, so what was in C? I had I part. No. Yes. Both B and C are I part, so this is useless. So what should I do? What should I do at this stage? Okay, let's try to do the polynomial part. So we have F part in A. So I'm going to multiply F part by I don't like that they use X again here. It's confused me terribly. So sorry if it's a bit if it looks a bit stupid, but I'm going to rename it because yep, it's disturbing me. Here we go. So feeling better now. So I will need F part in B because yeah, so I need F part in B, and for now F part is in A. So let's move F part in B. So now B equals F part. And I can load. Do I need to do that? Do I need to load the first constant in A? So that's 2, 3, 4, 5. 2, 3, 4. I forgot to add this. So that was add const of 0.5, which is constant number 4. That's x plus 0.5 in A. Okay, so here I'm using constant number 5. So that's A equals exp2p of 0. And so we can do the FMA now. Right, FMA 6, 7, 8, 9, 10. Yeah, the first one we loaded, and then we have 1, 2, 3, 4, 5 of them. And so that should leave us with A equals to the last one. Yeah, so it's fine. So that's yes, poly of poly part. That's why actually. And then I need to move this one away because I will do the ugly thing in A. So moving this guy in B so that I will be able to multiply it later. I'm moving in A the I part which was put in C. Is that right? Yes. I can do now the 2 power of int mul, and that should be exponentiation. I mean, exponentiation base 2. Maybe. Let's try it. Let's try it. So I'm gonna put it with the other ones over there. And then I'm going to write a test. So this was for the reference, and now I'm doing the same with yeah, let's pick this one, sigmoid, so it's exp2f, and I'm comparing to 2 f32 power f of x, and it's not ref, it's vm. Suspense. At least one that doesn't work out of the box. So now it's a bit reassuring. Okay. So what is it computing? So super negative value, which should be clamped and is not clamped. So we already have a problem here. Okay. Oh no, it's not a super negative value. It's a tiny negative value, nearly 0. So okay, let's go back to, I'm not sure which one is easiest to read to debug. I mean, we want to debug this one, so we might as well try to see if we're doing something obviously wrong. So moving our small x into B, that's okay. We're adding 0.5, so as we are in float and this is a super small value, then 0.5 wins. Alright, the floor is 0. expected. We're moving the integer part into C, which does nothing because it was already 0. We're then moving X in A, that's right here. We're moving B, which is what is B at this stage? B should be X. We're moving C into B. Yes, we're moving C into B, and C is I part, so it's 0. So we're doing a subtraction. Yes, we're doing the F part. So the F part is should be the small tiny value. Is that right? Yes, because we are supposed to have the fractional part between minus half and plus half. And so we keep our super small value. Then we're loading the first, so we're putting our tiny value in B. We are then loading the first constant, multiplying. So far, it looks pretty good. We're moving it out of the way. We're moving from C, the 0, 2 to the power of 0 is 1, and so the result is 0.69. Yes, and it's actually not the one which is wrong. This is the one which is wrong. And why is it wrong? Because something I don't understand. Okay, minimum, and so it fails for x equals 0. We're returning 0.69 for x equals 0, so that's definitely not correct. It should be 1, or it should be 1 or 2. No, it should be 1. Yeah, 2 to the power of 0 is 1, 2 to the power of 1 is 2. Okay. What is the value of the poly? Oh, okay. So the good thing is we have a reference implementation that works. So I can debug. Whoa, what I'm doing? Yes, okay. Y and 2 power of I part. So it's the x equals 0. Where is the debug? Yes, because I'm not calling the right function here. I mean, I'm not calling the reference implementation. So f exp2f of x. So y is 1 and 2 parts is 1. Yes, all right. So the problem is with the problem seems to be with the, oh yes, I know. I forgot one product. The final product plus 1, because I didn't put it in the constant, because 1, I already have it. So here I need to add FMA of 1. Yes. So we can compute exponentiation with 3 registers. I was sure I would need 4. And I'm not even using the swap BC in that one. So this is actually pretty fun. I mean, at least for me. But I'm going to stop because I'm tired. And we haven't done a lot of assembly yet, but I mean it's actually, yeah, I think it might be very interesting. I mean the good thing with exponentiation is I mean the fact that we managed to do exponentiation. We have a couple of functions that we have a couple more that works with exponentiation. So we have this guy, which is so this is a product disguised in a division. Exponentiation plus min and max, so nothing super complicated. This one also works with mostly an exponentiation. So the fact that we can do exponentiation with 3 registers means that there is probably much more of, I mean, there are a couple of these that we will be able to do. That one too we can do if we have exponentiation. I mean, maybe we need a 4th register, I'm not even sure. Because we can, so we need 3 registers to compute exp of x, and we need to keep x around. So we will need 4. We will need 4. But still, I mean, even if we need 4 registers, but I mean, it might be worth deciding that we do it for 4 because having the exponentiation gives us, let's say, 3 more. For this guy, we will need log, and log is, but I mean, soft plus, I'm pretty sure that, because there is another way. I mean, either we implement them on top of exponentiation, but soft plus is, it has to have a kind of, I mean, sigmoid is a big S, like that. Tan H is also a big S. So sigmoid goes from 0 to 1, and tanch goes from -1 to 1. But apart from that, it's super close functions. I mean, you can actually, I mean, there is an affine transformation that goes from sigmoid to tanch. Soft plus. Super. C'est quoi ça? What? Okay, soft plus is one more of these that goes 0 in the negative and x in the positive. So it's super close to relu. So there is gelu, don't know, and which have this kind of shape, and the R switch, the big the new kid on the block that one of my colleague wants. I mean, these are relu with a bulge, a negative bulge here. Yeah, there are actually, and oh yeah, Mish is a very, very ugly thing, if you want my opinion, because Mish is like tangent of log of exponentiation of, I mean, it's just crazy. But the thing is, this function can actually be approximated by rational functions. I mean, maybe not maybe not a rational function, but there is something. Maybe two rational function actually. Because the rational function are good approximation for function like which are big S, like sigmoid. If you do a polynomial, the problem with the polynomial is you never manage to get. I mean, it's super hard for a polynomial to flatten out when x grows because you have all these big power of x that will want to go crazy on the sides. So for this kind of function, a rational approximation when you have two polynomials of same degree divided by the other, you can actually manage to find pretty good approximation for this kind of function. I'm not too sure what would be the right model for hard soft plus for soft plus family. Because you need something that will stick to 0 in the negative and will converge to x on the positive. So maybe something times ReLU actually would work. I'm not sure. So my point is, why am I? If I'm trying to come back to where I was, the thing is, so this one we could rely on the rational approximation of Tanche with one more multiplication and one more multiplication. That one is kind of problematic if we don't have exponentiation and logarithm. That one, CLU, I'm not sure what is it's probably of the same family. So negative is 0 and positive is, I'm not sure what that is. CLU function. Come on, give me an image. CLU, okay, yeah, it's, so this one converge to -1 in the negative and x on the positive. So I'm not sure what to approximate it with. ELU is exponentiation. Yeah, ELU family. So negative 0, positive x. CLU will be more of the same. I guess one of these have to be all of them. ReLU, ELU. I mean, there are like a dozen of them. Yeah, a dozen. Like 3 times 4. So that's ELU. That's wish. This is so these two are the tangent and sigmoid. CLU is there. So 1, 2, 3, 4, 5, 6, 7, 8 of them are constant negative and x in the positive. Means parametric ReLU is a bit it had this alpha in the negative. So I mean, yeah, as I don't know if we can find something to approximate these functions, maybe the right way to compute them is to actually go through the exponentiation. We also need the log, which is a bit harder to compute than the exponentiation, if I remember correctly. I think you need, I think for the log, the right way to go is to also use one more rational approximation. And Mish is absolutely terrible. I mean, x times Tanche of log of exponential. I mean, come on, for something which basically has the same shape as Artswish. It's just crazy. Anyway, I'm going to stop. I'm going to stop for today. I am putting the videos on YouTube in case because I think Twitch, the VOD on Twitch for today will be split in 3 or 4 parts with the various interruptions. But I have a recording in two parts. I had to restart once because OBS was misbehaving, and but yeah, it will be easier to watch maybe fast forward because there was a bit of code. And next time I think we can start benching some of these implementation and start doing other implementation of the VM. For instance, we could start with with the vector primitives in Rust with intrinsics, because the portable SIMD doesn't work yet and may never work. Actually, I'm a bit I think it's a bit desperate at this stage. But what I mean, in any case, there is nothing difficult here to port to assembly. So this is probably the way to go. Will it be will it be performing super fast or not? I'm not sure, but I mean, it looks so simple, at least in ARM 8, that I definitely want to try it. So yep, going to do that next week or the week after. In the meantime, bye guys. If I found OBS, yep.